Buenos días, bienvenidos a la charla Diseño y consideraciones estadísticas en la implementación de ensayos clínicos, a cargo de la profesora Chari Messinger. La profesora Chari Messinger es profesora y directora de la División de Bioestadística, como directora de la Biostatistics Collaboration and Consulting Core en el Departamento de Ciencias de la Salud. Es profesora de la Facultad de Bioestadística de la Universidad de Miami en el Miller School of Medicine desde el 2002 y obtuvo su doctorado de la Universidad de Michigan. La doctora Messinger ha focalizado su investigación principalmente en la investigación en diabetes y tiene un extenso conocimiento y experiencia en la aplicación de metodología estadística y experticia en los ensayos clínicos en su diseño, tanto como en estudios observacionales. Thank you, Professor Messinger, for accepting our invitation.
Buenos días. Me siento muy honrada y agradecida por la invitación a Pasto para participar en este simposio tan especial. Entiendo que puede haber algunas personas en esta sesión de hoy que no sean de mi curso, así que intentaré presentarme nuevamente en español. Me llamo Sherry Messenger y soy mamá a 3 maravillosos jóvenes adultos, 3 perros y un gato. Estoy casada con un hombre maravilloso que me ha acompañado en este viaje a Pasto y me apasiona viajar y hacer ejercicio. Aunque hablo de español, lo he ido aprendiendo a lo largo de mi vida. Me siento más cómoda conversando de manera informal que dando una charla formal en este idioma. Por eso, tanto la conferencia como el curso los impartiré en inglés. Ahora, me gustaría contarles un poco sobre mi trayectoria profesional. Crecí en Florida, muy cerca de Miami, y realicé mis estudios de pregrado y maestría en ingeniería en la Universidad de Florida. Más adelante, continué mi formación con una segunda maestría y un doctorado en bioestadística en la Universidad de Michigan. En 2002, me incorporé a la Facultad de Medicina Miller de la Universidad de Miami en el Departamento de Ciencias de la Salud Pública. Ahí he trabajado desde entonces. Y actualmente soy profesora y directora de la División de Bioestadística y Bioinformática. Además, tengo el gusto de liderar un grupo colaborativo de bioestadísticos que apoya la investigación clínica y translacional en toda la institución. Además, enseño en los programas de posgrado en bioestadística y colaboro en las investigaciones clínica y translacional. Espero que ustedes me entendaron. Okay. From this point on, I'm going to speak in English. I'm hoping that you can understand the English. If I go too fast and you need me to slow down, please let me know. I have enormous respect for all of you being able to understand instruction in a second language. That is not something I have been able to accomplish yet. I would like to. Okay. Okay, so today's talk is going to focus on a domain that is both statistically rich and practically consequential, called implementation science trials. These trials aim to understand not just whether an intervention can work, but how we can get them to work reliably, equitably, and sustainably in the real world, not just in a laboratory setting or in an experiment. This focus places new demands on us as statisticians. Implementation trials routinely push against the boundaries of conventional design and analysis. They are often multi-level, longitudinal, and heterogeneous, and they may include multiple outcomes, adaptive elements, or non-standard missing data patterns. In this talk, I will walk through the most common statistical challenges we encounter in implementation trials. And I will highlight the methodological strategies that have emerged in response, from analytical and simulation-based power calculations to mediation and moderation in clustered data to Bayesian and adaptive frameworks. Those of you taking my course will get a much more in-depth instruction on these topics. Today will be an overview of the whole thing. I'll also share examples from real-world trials and some practical guidance on tools and software that can help us navigate these complexities. While the field of implementation science is often described using conceptual frameworks and qualitative insights, my goal today is to keep us firmly grounded in the quantitative core, the methods that help us translate implementation goals into rigorous, reproducible, and interpretable results. Okay, so this slide sets the stage for our entire session today. Implementation science is fundamentally about doing. It is not enough to know that an intervention works. We need to understand how to get it used, accepted, adapted, and sustained in what is really a messy real-world context of clinical and public health systems. That's where implementation science comes in. But implementation research cannot advance on conceptual frameworks alone. We need advanced biostatistical methods which are essential to ensure rigor, reproducibility, and insight. And that's why statisticians and bioinformaticians need a seat at the table early on, at the design stage, and throughout the life of an entire implementation study. The intersection between the implementation science and the statistics, it's not trivial. And we are asked to design studies that accomplish many things. We are asked to design them that respect organizational constraints and workflow realities, to accommodate multi-level interventions and nested data structures, to handle multiple outcomes that may include both subjective and objective measures, and produce results that are meaningful to clinicians, administrators, and policymakers, not just to researchers. In other words, implementation science stretches our toolkit. It asks us to go beyond standard linear models or two-arm randomized controlled trials and actually use simulation, Bayesian inference, mediation modeling, and/or cluster-level power calculations. It pushes us to think creatively, adaptively, and also iteratively. So in this session, I'm going to guide us through some of the most common and most complex statistical issues that arise in implementation research trials. We'll focus not only on the what, but on the how to select the right design, how to compute power, how to model mediation when data crosses multiple levels, and how to manage missingness that reflects organizational disruption and more. But most importantly, I want to reinforce this message. Implementation science is not less rigorous than efficacy trials. It's actually more complex, and it requires more statistical sophistication, not less. So let's begin by grounding ourselves in what implementation science actually is, how it's defined, and how it differs from more traditional trial approaches. Okay, so let's begin with a working definition of what is implementation science. It is the study of methods to promote the uptake of evidence-based interventions and practices in real-world settings. It is not just about whether something works. It's about how to get it used effectively and consistently in context. This includes things that are somewhat subjective, like understanding the barriers and facilitators to implementation. Things like leadership support, organizational climate, competing priorities, staff workload, even politics. Crucially, implementation science targets multiple types of outcomes. Yes, we still do care about the clinical outcomes, like blood pressure, viral suppression, tumor remission, but we're also deeply concerned with the implementation outcomes. Was the intervention delivered as intended? This is called fidelity. Was it acceptable to staff and patients? This is called acceptability. Was it sustainable over time? That's sustainability. These are the outcomes which require new measurement strategies and different statistical approaches. Many are multi-level, some are subjective, and most are influenced by both individual and organizational behavior. So this is where implementation science starts to diverge from what we might think of as classical clinical trials. and why statisticians play such a critical role in ensuring vigor, validity, and usefulness of the findings. Okay, so implementation science is a framework-driven field. These frameworks are more than academic. They serve as a scaffolding, in a way, for how we design, measure, and interpret our implementation efforts. Let's start with CFIR, the Consolidated Framework for Implementation Research, breaks implementation into 5 domains: intervention characteristics, outer setting, inner setting, and characteristics of the individuals involved, and the implementation process. For statisticians, CFIR is useful because it tells us what kind of variables we might need to collect and model. For example, contextual factors from the inner setting domain might be modeled as covariates or maybe even affect moderators of the intervention effect. Then there's re-aim, which prompts us to evaluate not just whether something works, but whether it's adopted, implemented with fidelity, and sustained. These domains translate directly into measurable outcomes that we need to account for in our analysis. Finally, the implementation outcomes framework helps us clearly separate implementation outcomes like fidelity or uptake from the clinical outcomes like symptom reduction or blood pressure, and service outcomes like access to care. This separation is critical when designing models with multiple outcomes or designing what to treat as a mediator versus an endpoint. These frameworks don't dictate the statistical model, but they do influence how we structure the data, select our outcomes, interpret missingness, and plan for multi-level or longitudinal analysis. Our job as statisticians is not just to analyze the data we're handed, but to help ensure that data collection and modeling strategies are grounded in a clear framework that reflects the study's scientific goals. So as we enter the core of today's talk, I want to pause for a minute and explicitly contrast implementation trials with what many of us think as the standard or efficacy-focused randomized control trials. So a classical randomized control trial, we all know what this is. This is what we might call an explanatory trial. And these are designed for internal validity. They have strict inclusion and exclusion criteria, very standardized delivery, and randomization at the individual level. The goal is to isolate the treatment effect under very controlled conditions. But implementation trials flip the script. They operate under real-world constraints. It gets messy, often in heterogeneous delivery systems, when the primary aim of testing strategies to promote uptake, fidelity, and sustainability of the interventions which are already shown to be effective. The shift brings several statistical consequences to the table. The first is that, as opposed to classical randomized control trials, randomization and implementation science usually occurs at the group or the cluster level, maybe by clinic, or by provider team, or by hospital team, or by school. And this creates correlated observations, requiring appropriate modeling to avoid underestimating the standard errors. Second, the outcomes of interest frequently span multiple levels and domains. For example, patient-level health outcomes alongside provider-level fidelity or system-level cost. And third, the environment can be dynamic. Implementation strategies are adapted in practice, stakeholders' behavior evolves, and the internal policies can shift even mid-study. So while the core principles of causal inference still apply, the design and the analysis of implementation trials demand flexible, multi-level, and often longitudinal thinking. It's a space where both theoretical development and applied savvy are needed together. Okay, so what kinds of statistical complexities show up again and again in implementation research? Let's briefly talk about this. The first, multi-level structure is ubiquitous. Individuals are nested within clinics, or systems. This nesting introduces non-independence, which needs to be accounted for in both the design and the analysis. So we'll talk about that. We'll introduce something called the intercorrelation structure and the analysis using methods like mixed models or just generalized estimating equations. Cluster level randomization often occurs with a limited number of clusters, increasing sensitivity to assumptions about correlation structure and variance components. Estimating these parameters reliably is very challenging and sometimes a source of controversy. Timing is complex. Interventions may be rolled out over time, as in a stepped wedge design, which I'll define soon, or adapted during delivery. This introduces what we call secular trends or carryover effects and unequal exposure, all of which complicate modeling and design considerations like power estimation. We often deal with multiple outcomes, many of them non-standard. Think about fidelity scores, cost measurements, satisfaction ratings, and adoption proportions. These may require multivariate modeling, generalized frameworks, or careful weighting across objectives. Missing data is rarely ignorable. It's one of those things we don't like to have to deal with, but it's rarely ignorable in this setting. Entire clusters may drop out. Data may be missing by design or not at random due to real-world constraints like staffing shortages or shifting institutional priorities. And finally, many implementation studies are moving towards what we call adaptive and Bayesian designs, especially when accrual of the data is slow, or prior information is very strong, or the need to respond in real time outweighs the benefits of fixed sample inference. Think about pandemic. Together, these challenges demand a statistical ecosystem that is adaptable, robust, and closely aligned with the practical realities of embedded research. So let's start with one of the most common designs in implementation science, the cluster randomized trial, or CRT. So CRTs are used when randomizing individuals isn't feasible or appropriate, often because the intervention itself targets providers or clinics or delivery systems, not just the patients. For example, training physicians in a new decision support protocol or changing the clinic workflow. In such cases, the unit of randomization is the clinic or the provider team. It's not the patient. So this immediately introduces what we call intra-class correlation. Outcomes from the individuals within the same cluster are correlated due to the shared context or exposure. That correlation must be accounted for in the design stage, think sample size, and analysis, think variance estimation. Even small intra-class correlations, say 0.01, can dramatically reduce the effective sample size if the cluster sizes are large. This is where the concept of design effects becomes crucial. For applied folks, that means we need to think carefully about how many clusters are required, how large they are, meaning how many people are within each cluster, and whether those sizes are balanced. For more theoretically inclined statisticians, the CRTs raise questions about variance component estimation, robustness of standard errors, and sensitivity to misspecification in hierarchical models. CRTs also highlight the importance of choosing the right analysis strategy. Mixed effects models are commonly used, but they rely on assumptions about random effect distributions, so they're largely parametric. GEEs provide a semi-parametric alternative, but they can yield biased standard errors with small cluster numbers. And when the number of clusters is small, permutation tests or randomization inference may actually be more appropriate. Cluster randomized trials are foundational in implementation work, but they are also fertile ground for methodologic refinement. They remind us that context, structure, and delivery matter as much as the treatment assignment itself. Note that ignoring this interclass correlation issue, it leads to underestimated standard errors and inflated type 1 error rates. So this is not something that can just be brushed under the rug. Okay, so I've said this term ICC or interclass correlation a lot. Now I'm going to define it. So this slide is foundational to understanding why cluster randomized trials and really any multi-level implementation design require different statistical handling than individually randomized trials. The ICC tells us how similar individuals are within the same cluster. You can think of it as the proportion of the total outcome variability that's explained by the between cluster differences rather than within cluster variation. For example, if patients within a clinic tend to have more similar outcomes than patients across clinics, perhaps due to shared staff, resources, or protocols, the ICC will be greater than 0. The higher the ICC, the more redundant the information we get from each additional person in a cluster. So the way I like to think about this when I teach this or when I'm trying to conceptualize it is I like to go to the most extreme scenario. If there's really no correlation between the people in the same cluster, then it's really just like having individuals that are independent across the entire study. If they are perfectly correlated, then it doesn't matter whether you have one individual in a cluster or 100, you're not getting any more information from having additional people within the cluster. Does that make sense? So from a modeling standpoint, ICC directly affects the design effect, which we'll talk more about in a few minutes. But the key point is if you ignore the ICC, you will overestimate your effective sample size and likely underpower your study. In implementation trials, ICC values are often modest. They're small. They're between 0.01 and 0.05 usually. But even these small values can drastically reduce the amount of independent information in the data, especially if you have few clusters, which are very large. Also important to know that the ICC can vary by outcome and by context. Clinical outcomes like blood pressure might have lower ICC than provider behaviors or documentation fidelity, which are more tightly tied to local practice environments. In practice, we often estimate the ICC from prior studies, pilot data, or even use ranges for sensitivity analysis, maybe in simulation. In Bayesian contexts, prior distributions over ICC are possible, but must be chosen with care. Overall, the ICC is one of the first things we need to quantify or bound when designing or reviewing an implementation trial. It's a small number, but it casts a very long statistical shadow. All right, so building on the ICC slide here, we're going to introduce something called the design effect, which is simple, but it's a powerful concept used to adjust the sample size calculations when you have clustered data. It essentially answers the question, how many more observations do I need to account for the clustering that I have in my design? So the formula is very straightforward. The design effect, this wasn't working before. Oh, there it is. Okay, so the design effect is 1 plus the cluster size minus 1, it's right up here, times the ICC. This quantifies how much the required sample size must be inflated to maintain statistical power when observations are correlated. So let's take a practical example. Imagine that you have 20 clusters, you have clusters of 20 individuals and an ICC of 0.02. That seems like a small ICC, right? So maybe you don't have to worry about it. But even then, the design effect would be calculated to be 1.38, meaning that you would need 38% more participants in the study compared to an individually randomized trial to maintain the same level of power. Importantly, the design effect increases linearly with ICC, but non-linearly with cluster size. So large clusters with even small ICCs can severely degrade power. This is why sample size planning in cluster randomized trials must always account for ICC and the design effect, and why simulation is often recommended when clusters vary in size or when other assumptions are uncertain. It also underscores why statisticians really need to be involved in these designs at the earliest of the planning stages. So those of you who work with implementation sciences, like especially in prevention trials or prevention sciences, you need to push yourself to be at the table early on so that you can design the studies right from the planning stages. These calculations influence recruitment targets, budget, and even feasibility. So this slide shifts from defining the problem to exploring solutions. Once we understand how ICC affects efficiency, the next question is, so what do we do about it? One of the most effective ways to reduce the impact of ICC is to increase the number of clusters. Not people within a cluster, the number of clusters. More clusters give us more independent units, which improves our power much more efficiently than increasing the number of individuals within a cluster. When increasing the cluster number isn't feasible, we can consider design strategies like stratified or matched pair randomization, which can improve balance and reduce residual between cluster variance. Including cluster-level covariates in the analysis, which helps us absorb between cluster heterogeneity and reduces unexplained ICC. Crossover designs are rare in this setting, but possible in some implementation settings. Or stepped wedge designs, which we're going to talk about next. These are not just statistical tricks. They are often necessary adaptations in constrained real-world studies. From a modeling standpoint, we typically use mixed effects models, which estimate random effects for clusters and correct standard errors. Alternatively, generalized estimating equations, or GEEs, are often used for population averaged effects, especially when the number of clusters is large. These modeling choices also depend on whether you're targeting cluster level or individual level inference, an important distinction that should be made during the analysis planning stages. Okay, so now that we've covered the basics of clustered randomized trials, let's turn to some advanced aspects that frequently arise in implementation science trials and which can significantly impact design and analysis decisions. First, multiple ICCs. In simple controlled randomized trial, we often assume a single intra-class correlation. But in many real-world implementation studies, the data structure can be more complex. You might have ICCs at several levels. For example, patients nested within providers or doctors. Providers nested within clinics or hospital systems. Or then even repeated measures over time. For example, patients treated by the same provider may have correlated outcomes, the provider level ICC, and those providers may be nested within clinics, the clinic level ICC, and then additionally, if that same patient is followed over time, you've got a time level ICC. When multiple sources of correlation exist, you need to use multi-level models that include random effects at each level, and the effective sample size must reflect this multi-source clustering. This is not just a technical detail. It severely affects power, type 1 error, and inference. Second, random slopes. Most cluster randomized trials models include a random intercept for a cluster, but often the clusters differ not only in their baseline levels, but also in their response to the intervention. This is especially true in implementation trials where context is highly variable. For instance, one clinic might experience a large fidelity improvement after training, while another shows only minimal change. Modeling this with random slopes allows for heterogeneity in the treatment effect across clusters. Statistically, this can increase realism, but it also complicates estimation and can reduce power. In Bayesian frameworks, you can also shrink these estimates towards the population mean using hierarchical priors, which is particularly helpful if you have a few clusters. Okay, third, crossed versus nested designs. We often assume a clean hierarchy. Patients nested within providers, providers nested within clinics, but in practice, things are often quite a bit messier. Providers may rotate across clinics, or patients may see multiple providers, which creates a crossed structure, not purely nested. These designs violate the assumptions of standard hierarchical models and require crossed randomization effects models, which can be computationally demanding and harder to converge, especially in small samples. Ignoring the structure can lead to biased variance estimates or incorrect inferences, especially if one of the crossed levels has a strong influence on the outcomes. Partial nesting occurs when some individuals are nested within clusters and others are not. This commonly arises in group-based interventions where one arm is clustered and the other is not. For instance, group therapy versus individual treatment. This creates non-parallel correlation structures, which invalidates standard clustered randomized trial modeling assumptions. So you'll need to use models that allow for differential variance structures across arms, such as specifying random effects only for the clustered arm or using variance components by treatment group. This partial nesting is a major reason why statisticians need to be brought in early during trial planning, because assumptions about exchangeability and independence no longer hold. These four complexities we've talked about, multiple ICCs, random slopes, cross designs, and partial nesting, are common in modern implementation research studies. They are not flaws, they are features of real-world delivery systems. They require us as quantitative scientists to bring both technical depth and collaborative clarity to the table, ensuring that study designs and analytic models reflect reality, not just simplicity. Okay. So now I'm going to introduce the stepped wedge design. Anyone here heard of the stepped wedge design before? No. Okay. So stepped wedge designs have become increasingly popular in implementation science because they address both ethical and logistical concerns. Oops. There we go. Okay, so stepped wedge designs have become increasingly popular because they address both ethical and logistical concerns that arise in real-world trials. In this design, all clusters eventually receive the intervention, but they do so at different time points. As you can imagine, the fact that every cluster eventually gets the new intervention, that's an attractive feature. That's a feature that gets providers to want to participate. The order in which clusters receive the intervention is what is determined randomly. This preserves the internal validity of a randomized trial. This staggered rollout allows each cluster to act as its own control, meaning we can compare outcomes in the same cluster before and after the intervention is implemented. This is especially helpful when between cluster variability is high. Stepped wedge designs are commonly used when it is not ethical to withhold an intervention from any group permanently. For example, if a hospital system wants to implement a new infection control protocol, delaying the rollout may be acceptable, but denying it altogether is not. This design is time-based, which brings in added statistical complexity that I'm going to cover in the next few slides. So analyzing stepped wedge designs is more complicated than standardized cluster randomized trials for several reasons. The biggest challenge is confounding by time. Because all clusters eventually receive the intervention, we must distinguish between changes due to the intervention and changes due to secular trends, things that would have happened anyway over time. That's why statistical models include fixed or random effects for time, depending on assumptions. We also need to adjust for repeated observations within clusters, often using generalized linear mixed models or GEEs to account for correlation. In small sample settings or with irregular intervals, Bayesian models offer flexibility in incorporating prior information and stabilizing estimates. Ultimately, stepped wedge designs require careful modeling of both time and cluster level effects to avoid biased estimates of the intervention effect. Power and sample size calculations for a step wedge trial can be very challenging. Because of the repeated measures and the staggered intervention timing, standard cluster randomized trial sample size formulas won't apply. Power depends on the number of clusters, number of steps or time points, and the cluster size per step. But it also depends on this ICC, and critically, the within-cluster correlation over time. In practice, a design with few clusters and many time periods may perform very differently than one with many clusters and fewer time points. Closed-form approximations might exist, but they rely on simplifying assumptions. That's why simulation-based power estimation is often used in this kind of a trial. It allows us to incorporate real-world characteristics such as dropout, irregular cluster sizes, or staggered recruitment. It's essential that power analysis be done early in the planning and that they're transparent, because assumptions about ICC, timing, and cluster size can substantially affect feasibility. So this is a classic stepped wedge design. Along the vertical axis, we have clusters, and then along the horizontal axis, we have time periods. These could represent months or quarters, while the clusters can represent hospital, clinics, schools, or regions. Each cell in the grid represents whether a given cluster is representing the control, which is in the white, or the intervention, which is in the dark blue. In period 1, all clusters are in the control phase. Then at each successive step, one additional cluster transitions into the intervention phase. By period 7, all clusters are receiving the intervention. This rollout allows us to compare outcomes within cluster over time. Each cluster acts as its own control before receiving the intervention. It also lets us estimate time trends and intervention effects, while ensuring that no group is permanently denied this intervention. But the design introduces statistical complexity, including potentially confounding by time, cluster period interaction, and autocorrelation within clusters over time, which we will tackle in the next slide. So hybrid trials are a hallmark of implementation science, especially when we want to accelerate translation from evidence to practice. Rather than doing a clinical trial first, followed by a separate implementation study, hybrid trials allow us to attack both sets of questions at once. These trials are categorized by type. Type 1 is like a traditional clinical trial. The main objective is to determine if the intervention works. Type 2 gives equal weight to the effectiveness and the implementation outcomes. And type 3 flips the emphasis to where we're more interested in evaluating the implementation strategies, like comparing two methods of training clinicians, while still tracking clinical outcomes to ensure there's no harm. From a statistical perspective, hybrid designs are challenging. You may be dealing with correlated outcomes like fidelity at the provider level and symptom improvement at the patient level, or even multi-level structure where patients are nested within providers or clinics. You might also need multivariate generalized linear mixed models, joint models, or mediation analysis. These trials require large sample sizes and should align with implementation frameworks. Implementation science trials measure multiple outcomes, so we need to use methods of analysis that handle this well. The challenge is that these outcomes may be on different scales: binary, continuous, ordinal. They may be correlated, and they may be at different levels. Statistically, this means we need to consider joint modeling approaches, such as multivariate regression, structural equation modeling, or multi-level generalized linear mixed models. Let's talk a little bit about power and sample size, starting with analytic approaches. For cluster randomized trials, we often use closed-form formulas that incorporate ICC, cluster size, number of clusters, and the effect size. These formulas are typically extensions of those used in individually randomized trials. But for more complex designs, such as stepped wedge trials or hybrid trials, analytical formulas don't exist. However, simulation is often the preferred method when these designs get more complex. So simulation-based power calculations can be used when designs are complicated, and it's a critical tool for power and sample size planning. The idea is to create synthetic data sets that mimic your planned study under a range of assumptions that you think might really be feasible, that you might see, and then estimate the power empirically by fitting the intended analytic approach to simulated data. This helps identify underpowered designs that might look sufficient on paper and allows us to evaluate model performance under conditions that deviate from ideal assumptions. There are R packages like step wedge SWCRT design and cluster power, which are particularly helpful. A little bit about missing data. It's inevitable. It happens, especially in implementation science trials, and it tends to be more complex than tightly controlled efficacy studies. We often see multi-level missingness. For example, an entire cluster might drop out, like if a clinic closes, or some providers or patients may have incomplete data. The missing data may not be at random, so it's not ignorable. And in hybrid and step wedge designs, missing can vary by time. So this sets up our need for advanced methods of analysis and thoughtful pre-specification. So here we move beyond basic handling of missing data, and it's important to select methods that reflect the multi-level and temporal complexity of implementation trials. Multi-level imputation is one approach. Bayes methods offer additional flexibility. Inverse probability weighting is another option, especially useful when we can model the probability of missingness. And sensitivity analyses are crucial, especially under the potential missing not at random. Okay, now I'm going to talk a little bit about moderation and effect modification. Moderators allow us to examine whether the effect of an intervention differs across subgroups or settings. In implementation science, this might include contextual factors like leadership support, clinic size, or provider training. Moderation is typically tested using interaction terms. Multi-level models are essential when data are nested, and it's important to pre-specify a small number of plausible moderators based on theory or prior work. Over-testing can lead to spurious findings, as we all know, especially in small trials. This breaks down key concepts involved in moderation and effect modification in implementation science with a focus on real-world context. Contextual moderators include variables that define the setting or environment, the context in which the intervention is implemented. For example, clinic size, rural or urban setting. We have cross-level interactions. This occurs when an effect is measured at one level, like the patient level, and that is modified by characteristics from a higher level, like the clinic or the provider level. For example, imagine that we're evaluating a behavioral health intervention delivered to patients. We might find that patient outcomes improve more in clinics with high implementation climates. This suggests the effectiveness of the patient-level intervention depends on some higher-level contextual feature. So we're using interaction to be able to incorporate these contextual variables. So a little bit on mediation versus effect modification. These are both things that are important in this setting. Mediation helps us understand how or why an intervention works. It looks at the mechanism that connects the intervention to the outcome. For example, in an implementation trial of a provider reminder system, we might hypothesize that the system improves provider fidelity, and fidelity leads to better patient outcomes. Here, fidelity is the mediator. It's the means by which the mechanism of action occurs. Statistically, mediation analysis involves decomposing the total effect of an intervention into a direct effect and an indirect effect that goes through the mediator. So to summarize, mediation is about pathways and mechanisms. Moderation and effect modification are about context and conditions which differentially affect the outcome. In implementation science, both are crucial. So this slide focuses on mediation in the context of multi-level implementation science, where we want to understand how an implementation strategy leads to improved outcomes. So the first is the intervention. This is the implementation process. It might be an implementation strategy like audit feedback to providers. This strategy is hypothesized to improve the implementation process. The implementation process leads to the clinical outcome. We want to test whether this implementation improvement translates into downstream clinical outcomes. We need methods that can handle mediation in nested or clustered designs. This is just a picture of how audit and feedback increases provider fidelity, which improves patient A1C levels in an implementation trial for type 1 diabetes. What you see here in the dashed line is the direct effect that does not go through the mediator. So it bypasses the mediation. Whoops. A little bit on Bayesian methods, which are gaining traction in implementation science because they offer a flexible framework for analyzing complex, messy, and hierarchical data. This is very useful in implementation research where data structures often are multi-level and the number of clusters may be small. Bayesian models are well suited for analyzing stepped wedge and cluster randomized trials, for integrating expert knowledge, and for evaluating nuanced implementation outcomes where standard models may be underpowered or unreliable. So this is just an example, and if you want my notes afterwards, I'm happy to share them, of the R code, which uses a special package in R called BRMS, the Bayesian Regression Models Using STAN, to fit a Bayesian hierarchical model that handles binary outcomes. Here we're analyzing a cluster randomized trial where patients are nested within clinics. The formula specifies a random intercept for clinic and a treatment effect. These priors are weakly informative, a normal 0.2 for the treatment effect and a Cauchy 0.1 for the cluster level variance. The model runs for 4,000 iterations across 4 chains and provides a high-level interface to STAN, allowing flexible Bayesian estimation. This plot shows a prior distribution, which is dashed, centered at 0, and the posterior distribution, which is solid, centered at 1.2. The posterior reflects updated beliefs after seeing the data. The shaded region to the right of 0 represents the probability that the treatment effect is greater than 0. This is a key strength of Bayesian inference. We can make direct probability statements about parameters. So with Bayesian methods, we can incorporate prior knowledge or historical data, enabling more stable inference, particularly for variance components. In cluster randomizer stepped wedge designs, for instance, we may have only 10 to 20 clusters, too few for reliable frequentist estimation. So Bayesian modeling is well suited for multi-level implementation data. If we want to estimate the effect of an audit and feedback strategy on provider adherence, a Bayesian model estimates the full posterior distribution, accounting for the between cluster variability. A major advantage of Bayesian models is their ability to incorporate missing data directly. That's pretty cool. Bayesian models integrate this over uncertainty and do not rely on imputation. This is critical in implementation science trials where missingness may be structured or informative. So Bayesian methods require careful prior selection. Vague priors can still bias results in small samples, so we have to be very careful about this. Make sure to document priors and check convergence thoroughly. Okay, so this is a mini case study that illustrates a common scenario in implementation science. A small cluster randomized trial evaluating a new telehealth training for providers with only 10 clinics. Traditional frequentist approaches would struggle to provide stable estimates. Here, a Bayesian model is used with a weakly informative prior centered at a small positive effect. based on pilot data. Hierarchical models here are used to borrow strength across clinics, accounting for variability in baseline readiness. This is both intuitive for stakeholders and more informative than a binary p-value. Okay, in what's left, I'm going to talk a little bit about adaptive designs and implementation science. Implementation science often operates in environments that are dynamic and unpredictable. Clinics may undergo policy shifts, provider turnover, or health system restructuring. Adaptive designs allow us to revise study elements like sample size, randomization ratios, or intervention arms based on interim data. For example, adaptive randomization means that the probability of being assigned to an arm increases if interim results suggest that that arm is performing better. That's attractive because people are more likely to get randomized to things that seem to be working. Covariate adaptive randomization is where we dynamically balance on clinic size or baseline fidelity to ensure we aren't unintentionally stacking clusters with different readiness levels into a single arm. We often face uncertain interclass correlation coefficients and then use something called adaptive sample size re-estimation, which helps us recalculate sample size mid-study if the design effect is higher than expected. You may also consider dropping arms if an interim result suggests they're not working, or adding arms. This slide introduces SMART trials, which is a type of adaptive trial. It's sequential, multiple assignment randomized trials, which are increasingly common in implementation science. They're designed to reflect how interventions are actually adapted in practice. In this example, you start by randomized clinics into two initial settings, right here. So you randomize them into two initial settings, and then after a pre-specified duration, maybe 6 months, you assess their implementation response. Clinics that are not improving as expected are re-randomized to a more intensive strategy. This allows us to learn not just what works, but what to do if it doesn't. The statistical challenges include needing specialized methods for analyzing dynamic treatment regimes, often relying on nested randomization structures and handling multiple comparisons or sequencing effects. So here's an example of adaptive randomization. Unlike SMART trials, where randomization happens in stages, here randomization probabilities themselves evolve. So the results suggest that one implementation strategy is outperforming the other, for example, better staff fidelity to a new clinical protocol, then more sites or participants can be randomized to that arm. This can be done using response adaptive or covariate adaptive algorithms. It does add statistical and logistical complexity, particularly in real-world implementation trials with delayed outcomes and messy fidelity data, pretty much most of them. This is a little bit on whoops. All right, I didn't change the slide before I was supposed to. This is a little bit on software and workflow. I'm not going to go into the weeds here, but there is, this highlights some of the key tools and platform-specific packages that we rely on for statistical modeling in this area, especially those with complex multi-level or longitudinal structures. So there's R software, for example LME4, GLMMTMB, and GPAC. These are commonly used for modeling multi-level data. LME4 is the go-to for linear and generalized linear mixed models, while GLMMTMB extends this with more distributions and maybe zero inflation. GPAC is used for GEE. There are design tools, there's imputation strategies, all within this framework. And there's also packages in SAS and in Stata which do the same thing. Proc Mixed, Proc Lim Mix, Proc Gen Mod. These are the parallel options in SAS. So some best practices in the design phase involve biostatisticians early. If you're working with a group that does implementation science, encourage them to involve you at the very beginning, not after the data is collected. It would be too late. The design of the study has to be correct, and it has to incorporate planning for the power and sample size considerations and the analytic approach. Pilot and feasibility studies are crucial in estimating ICC, gauging likely effect sizing, and stakeholder input helps us understand which outcomes matter for providers, and we can align our design with real-world feasibility. So this slide outlines best practices for the analysis phase. Start simple and build complexity intentionally. Begin with something simple like a random intercept model, then consider adding complexity like random slopes and see whether or not the model fits better. Jumping directly into complex models can lead to convergence issues or misinterpretation. So this is my last slide. It highlights emerging areas of innovation and opportunity in the statistical design and analysis and implementation science trials. These future directions reflect how the field is evolving in response to real-world complexity. In implementation trial, testing different models of behavioral health integration, for example, a platform design could let investigators test multiple delivery models and add new ones as policies or technologies shift. And that is it. I end with a cartoon. This is an important cartoon. The implementation gap, it refers to the difference between evidence of what works in theory and what is delivered in practice. So if you think about it, you might have a treatment that works really well in theory, but if it's actually not delivered in practice, it's useless. What good is it? So implementation science is all about addressing that gap. That's it. That's it. Yeah. Okay. Are there any questions? Okay, I've got one.
Bueno, igual esto ya no se pueden hacerlo.
That nowadays are using this implementation science to study some disease or.
So yes, so the first question, implementation research, implementation science trials are more of a newer area of research. It's a way to be able to incorporate the implementation because as we can see, just proving that something is efficacious is not enough. Efficacious is what we know from a controlled setting, like in a randomized controlled trial or in a lab, right? And then efficacy is more about, effectiveness is more about what happens in the real world. But even in a controlled setting, you're not going to be able to really know what happens in the real world with effectiveness. In the past, this is always what was referred to as phase 4 clinical trial, which is post-market. Right? But then that's subject to a lot of bias with how do we collect that data. That's more observational. So implementation science is a field of research that looks to be able to address the questions of effectiveness from the beginning by putting these things into real-world settings. The problem with it is that the real-world settings are messy. They're just so hard to deal with. So we need to think about what are the designs, what are the issues in the design, what are the statistical approaches that can help us deal with things like bias or efficiencies, what are the contextual factors, like rural environments versus urban environments versus people of different socioeconomic levels and how that affects their access to care, and how do we incorporate those. So it's more of a newer field that's becoming more and more popular, and more statisticians are now getting involved in trying to think about methodology that helps address some of these problems. The real world examples I actually do, and I'd be happy to talk to you more about some of the things that I'm doing personally in this area, but in my course, I do bring in some real world examples and published papers. So if you want, just reach out to me and I'm happy to email you some of those as well. Okay? Any more? Okay, I know we started late and that's why we went over, but I did keep myself at 45 minutes, I think, so I think we're okay. That's it. Thank you all for your time.
Muchas gracias. Sí, ahorita ya terminó la transmisión.
¿Cuándo?
En este momento.
Okay.
Sí, o sea,
Good.
hasta la pregunta.
Okay, gracias. my slides? Please tell me. Don't let me do that. I have to remember to do it in both places. Okay, so today our focus is going to be on clustered and longitudinal designs. All right, so let's ask the question, why do we cluster randomize? Let's unpack each of these points one at a time, as they're especially relevant in implementation science, where we're often intervening not on patients directly, but on clinics or health systems. The first is to reduce contamination risk. In traditional randomized control trials, we try to keep the treatment and control groups separate. But in the real world, like hospitals or schools, people talk. Providers serve multiple patients, and it's really hard to prevent sharing of practices. That spillover is what we call contamination. Randomizing whole clusters like clinics or provider teams helps us avoid that problem. The second is to align with intervention delivery. Many implementation strategies like staff training or clinic workflow design or changes in electronic health records can't be delivered at the individual level, so it wouldn't make sense to train half of the providers in a clinic and not the others. So we randomize at the level the intervention is applied, and this mimics more what the real world would look like. This makes the implementation realistic and reflects the way care is delivered in practice. For ethical and practical considerations, sometimes randomizing individuals simply isn't possible, or is it ethical? Imagine giving some patients access to a new mental health resource while withholding it from others in the same clinic. It can cause confusion, perceptions of unfairness, or anger. So the infrastructure to support two parallel care models in a clinic may just not exist. Cluster randomization respects the operational constraints and supports equity within units of care delivery. Okay, so cluster randomized trials have some unique design features that we have to plan for carefully. The first is the randomization at the group level. In cluster randomized trials, we randomize groups like clinics or schools, not individuals, and this matches our level of intervention delivery. The outcome, though, is measured at the individual level. So although we assign at the cluster level, we often collect outcomes at the individual level. For example, patient satisfaction, or hemoglobin A1C, or medication adherence. This creates a nested structure which has implications for both analysis and interpretation. It also requires what we call a design effect adjustment, because individuals within the same cluster are more alike than those in different clusters. We have to adjust both power calculations and our methodology of analysis for this clustering. This is where the interclass correlation coefficient comes in, and I ended last time just barely touching on what this is. Even small ICCs can have a large impact, especially with large cluster sizes. The design effect tells us how much our sample size needs to be inflated to account for this. So let's define the ICC more precisely. The interclass correlation coefficient tells us how strongly outcomes are correlated among individuals in the same cluster, such as patients within the same clinic or students within the same school. Conceptually, what this does is it measures the proportion of the total outcome variability that's explained by difference between clusters rather than within clusters. The formula is ICC equals the between cluster variability over the sum of the two sources of variability, both between cluster and within cluster variability. If the between cluster variance is very large with respect to the total variance, this ratio will approach 1, so the ICC approaches 1. And this would mean that individuals within the same cluster are very similar to each other. If the between cluster variance is very small, this quantity approaches 0. individuals within a cluster are no more similar to each other than they are across clusters. In a cluster randomized trial, the ICC is used to adjust the sample size through what is called the design effect. And this compensates for the reduced effective sample size due to within cluster correlation. It helps guide model choice, such as using mixed effects models or GEEs, to account for clustering in the analysis in a way which appropriately estimates standard errors of treatment effects. Even small ICC values, like in the range of 0.01 to 0.05, which is pretty typical in implementation science trials, can have a large effect on study power, especially when cluster sizes are very large. So in summary, ICC is a core parameter for designing and analyzing implementation trials using cluster randomization. So this is a slide which lets us kind of understand a little bit more about intra-class correlation. When it's low, individuals within a cluster vary widely. So you see larger variance here with low ICC, like patients in a clinic who respond very differently to care. This means we get a lot of independent information from each person. But when the ICC is high, like in this side, we're not getting a lot of independent information from each person. People in the same cluster are very similar to each other, like classrooms where all students score about the same, regardless of the intervention. That similarity means we're getting less new information per individual because the responses are more predictable from the cluster they belong to. This matters because high ICC inflates the design effect, which is the adjustment we make to account for clustering. It means we need more participants to maintain statistical power, since we're not gaining so much from each individual subject. Okay, so the design effect formula. In a cluster randomized trial, we have to adjust for the fact that we have ICC, individuals from each cluster are correlated. So this design effect formula tells us how much we need to inflate our sample size in order to be able to have the same power that we would have had if it was an individually randomized trial. I see some of you taking pictures of my slides. You can, but they're also available for you to download. So, and if you can't find it, just email me, I will give it to you. So I don't want you to have to worry about that. So the design effect formula is given right here, where M is the average number of individuals per cluster, and the ICC is that intra-class correlation coefficient. So let's say we plan to recruit 20 patients per clinic. The estimated ICC is 0.05. Then the design effect we would calculate by plugging in 20 here, and the ICC is 0.05, and you're going to end up with 1.95. This means the sample size needs to be almost doubled to achieve the same statistical power as if the observations were independent. That's pretty huge. That's pretty significant. If you originally needed 100 patients for an individually randomized trial, you would now need 195 participants to have the same power. This concept is essential in implementation science, and we often deal with interventions that are delivered at the clinic or system level, so we have to account for correlated outcomes. Also, the impact of ICC grows with larger cluster sizes. Even small ICCs, like 0.01, could lead to substantial inflation if clusters are large, meaning that number is large, the number per cluster. Okay, so walking through a design effect. This is the one I just described. Suppose you're planning a study where you have 20 patients and you estimate the ICC to be 0.05. This is what I just described. That design effect becomes 1.95, so we need twice the number of participants. So this slide shows us how the design effect increases as ICC and cluster increase. So on the x-axis, we see that we have ICC values ranging from 0 to 0.2. Each of these lines, or these curves rather, you can't really tell they're curved, but they are, each of these represents a different average cluster size. So we have M equals 5, 10, 20, or 50, 5, 10, 50, and then up to 100. for the cluster sizes. And you can see that even small ICCs lead to noticeable inflation when cluster sizes are large. For example, at an ICC of 0.05 and M equal 100, so ICC of 0.05 and M equal 100, we're about here, right? The design effect is nearly 6. Where if the ICC is 0.1 and M equals 100, so we have ICC of 0.1, M equals 100, okay? The design effect is very large. This illustrates why it's so important to conduct sensitivity analysis during the trial planning. Using too low of an estimate of an ICC or underestimating the cluster size can lead to underpowered studies. There it is, a 0.01, and then the M is 100. We still have a design effect more than 2. So it does increase. And again, this depends on the cluster size as well as the ICC. So this is an example, again, my notes, these are all going to be available to you. It's an R code that walks through the process of calculating the design effect and adjusting sample size accordingly. So you have to tell me if I do that, please. The R code walks through the process of calculating the design effect and adjusting your sample size accordingly. We define the average cluster size first. Here it's M equals 20 by definition, and an estimated ICC. And as you can probably already imagine, you can do this over multiple scenarios to see how the design effect changes. The design effect formula is then applied right here. And if you originally calculated a sample size of 100 for individually randomized trial, in this example, which we've gone through, you would end up with 195 participants needed. This simple code is useful not just for planning, but also sensitivity analysis, testing how does that required sample size change if my ICC changes, is different than what I'm thinking it might be, or if I increase or decrease cluster sizes. So this helps plan studies. This graph visually demonstrates the impact of intra-class correlation on the effective sample size in a cluster randomized trial, assuming an average cluster size of 30. The x-axis shows the ICC values from 0 to 0.2, and the y-axis shows the effective sample size as a proportion of the actual sample size. So when the ICC is 0, the effective sample size is equal to the actual sample size, but then as the ICC increases, individuals within clusters contribute less independent information. At an ICC of 0.05, you're already down to about 40% effective sample size, right? At an ICC of 0.1, it's closer to 30%, and at an ICC of 0.2, you retain only about 10% of the effective information. This loss is because individuals within a cluster are correlated. Think about if it's extreme, if the ICC is 1. You're getting the same information over and over again, so it does not help you to have more people per cluster, right? So the takeaway is that even small ICCs can drastically affect power. That's why estimating ICC and applying the design effect is essential in planning a cluster randomized trial. And in implementation science, we're usually working with clusters like clinics or schools, so it's very important to consider this. Okay, so this is some R code that helps calculate the ICC and design effect. It uses a package called ICBear, right? And it's a package from the ICC pack. It's a function from the ICC package. I apologize. The package is ICC. ICCBear is the function, and it's used to estimate the intra-class correlation coefficient directly from your data set. So you need two pieces of information. The clustering variable, this defines your groupings, like the clinic ID, and a numeric outcome variable, something like blood pressure or satisfaction scores. This ICC tells us how much of the variation in the outcome is due to differences in clusters. And this is a simple example of how to calculate the intra-class correlation coefficient and the design effect. So we can use this ICCBear function from the ICC package, to estimate the ICC based on clustering, a clustering variable in our data and an outcome variable in preliminary data. Then we define M as the average cluster size. This is the design effect is calculated using the formula for the design effect, and it tells us how much our sample size should be inflated to account for clustering, using information from preliminary data to understand correlation structures in our cluster design. So this example again shows how a seemingly small ICC can significantly inflate the required sample size. Say your original power calculation, assuming a 2-arm clinical trial with individual randomization, you need 200 individuals per arm. Once you realize the intervention has to be cluster randomized, let's say with an ICC of 0.05 and a cluster size averaging about 30, we apply the design effect and we see that we need 2.45 times the number of participants per arm, which is 490 participants per arm. It's essential to factor this in early, obviously, otherwise you end up with an underpowered study and a waste of everybody's time and money and resources. So this has to be factored in when budgeting and planning studies from the very beginning. So to calculate the average cluster size needed for the design effect, it's very simple. We just simply calculate the number of individuals in each cluster and take the average. You can do this very simply in R using mean functions, or you can use tapply or dply or group by with the summarize function if you're using tidyverse. The step is ridiculously simple, but it's so necessary because the design effect depends on how big clusters are on average. And so this is a complete R example demonstrating ICC estimation and design effect all in one swoop where we have differing cluster sizes. Here there's a simulation of 10 clinics, each with 20 individuals, and each clinic has a slightly different mean, and individual outcomes vary around that. We can even see the cluster sizes are simulated to be different. We then estimate the ICC using ICC-Bear and calculate the average cluster size using the table or mean function. This code mirrors what you would do with real data, simply swap in your actual clusters and outcome variables. Very simple. Okay. Let's talk about simple randomization and cluster randomized trials. Simple randomization in a cluster randomized trial means that each cluster is assigned independently to an arm with no stratification or matching. This is one design. The approach is very straightforward and easy to implement, especially, and I'm going to say really only, when you have a large number of clusters. In implementation science, we often work with a small number of clusters, sometimes fewer than 20 in total. In that case, simple randomization can lead to imbalance between treatment arms on important covariates like clinic size, or percent insured, or baseline performance, or geographic region. These imbalances can compromise the internal validity and reduce power. You may also lose credibility with stakeholders if one group looks better than the other before the intervention is even starting. So while simple randomization is conceptually simple, it is rarely the best choice for a cluster randomized trial with small numbers. We often prefer stratified randomization or pair-matched designs in these cases. So stratified randomization, you're probably familiar with this in the context of a simple individually randomized trial, right? So it's a straightforward way to ensure balance across important covariates when you have a small to moderate number of clusters. You divide the clusters into strata, for example, by region, urban versus rural, or by size, small versus large. Then you randomize the clusters within each stratum. Why do we care? Why do we think that small versus large might be an issue? It might really be a marker of something else, like the socioeconomic status of the people surrounding that clinic, right? And having more infrastructure within. This increases the chance that each arm of the trial has similar characteristics at baseline. It's relatively easy to implement when you have few stratifying variables, but becomes much harder if you have many covariates to balance because you may end up with very small or very empty strata. So stratified randomization, again, is a very straightforward way of doing this. This is some code to be able to look at stratified randomization. In this example, we have 20 clusters and stratified by region, urban versus rural, which might be associated with baseline differences in care delivery or patient demographics. We then randomize within each of these stratum. So within the 10 urban clusters, we randomly assign 5 to intervention and 5 to control. We do the same thing for the rural clusters. This process ensures that each treatment arm has comparable number of urban and rural clusters. This improves balance and power. You can stratify by multiple factors, but we have to be careful because the number of strata grows very quickly, and you risk ending up with very empty or small strata. So ideally, limit to 1 or 2 stratification factors. This technique is very easy to implement in R using subsetting and the sample function as shown. So you have access to all this code. Matched pair randomization is best when the number of clusters is very small. You carefully match the clusters into pairs based on key characteristics like size, location, or baseline outcome, and then randomize within each pair. This method ensures a high degree of balance across trial arms. It can also improve power and reduce variability in estimation. However, it does require careful matching, and you must account for the matching in analysis, usually by using paired statistical models like conditional logistic regression for binary outcomes or blocking and mixed models. Always, the analytic strategy should match the design. So this slide illustrates matched pair randomization in R, commonly used in cluster randomized trials. Here we simulate a cluster level covariate like size, sort the clusters, and then form matched pairs. Within each pair, we randomly assign one cluster to control and the other to intervention. This approach increases power by ensuring balance across the covariates that may impact outcomes. And this slide explains how the matched pair randomization code might be useful in different contexts. In simulation studies, our goal is often to understand how the matched pair design will affect power, bias, or type 1 error under various scenarios. So we change the assumptions and we simulate. We would use the code to simulate covariates for each cluster, form matched pairs, and then assign treatment randomly within pairs, and then simulate the outcome data conditional on the treatment and cluster features. You would repeat this many times and analyze the results to assess average performance. In actual trial preparation, the code is used to match clusters based on real baseline covariates, like clinic size, geographic region, or prior outcomes. After assigning pairs and randomizing, these assignments should be saved and finalized. These assignments are often used to allocate treatment in the real study. In analysis, pair membership is included as a blocking variable. This approach is especially useful in small trials where random imbalances across treatment arms can substantially impact inference. And then we have covariate constrained randomization, which is a more advanced technique designed to ensure balance across several important covariates in trials with a small number of clusters. Here's how it works. You pre-specify the covariates you want balanced. For example, baseline outcome rates, cluster size, region, or prior implementation readiness. You then generate a large number of possible randomizations, sometimes thousands or more, and calculate an imbalance metric for each one. You then select one of the best randomizations based on the metric, typically those in the top X% or so of balance, either randomly or deterministically. And this approach avoids the pitfalls of chance imbalance without the restrictions of strict matching, and allows you to incorporate more covariates than stratification or pairing would be able to handle. It's increasingly popular and pragmatic in implementation trials where fairness and efficiency are both critical. However, it does require advanced planning and reproducibility, including setting a random seed and fully documenting procedures. So again, I'm providing some R code for this. I know I don't expect you to be able to see that. That's why I'm going to give it to you later. It's a lot of code, but focus on this, what the code does. So this method simulates a large number of possible randomizations and uses a quantitative criterion. Here it uses a standardized mean difference as the metric for imbalance. It's especially helpful in small cluster randomized trials with many cluster level covariates. Unlike stratification or matching, this method handles multiple continuous and categorical variables at once. But you must document the exact covariates used, the imbalance metric, and the random seed and code for reproducibility. So this is a summary slide that compares the 4 major randomization strategies used in cluster randomized trials. The choice among them really depends heavily on the number of clusters, the importance of covariate balance, and the complexity you're willing to manage in trial design. So it goes through all of them. You can go through simple randomization, which is the most basic. It works fine when you have a large number of clusters because imbalances tend to wash each other out. In small cluster randomized trial, it often leads to major imbalance. Stratified randomization are where we stratify the groups by important characteristics. This is great when you have a moderate number of clusters and few clearly important variables to control for. That's my go-to, stratified randomization, when I have very few stratification factors and enough clusters to make it worthwhile. Matched pair randomization is ideal when you have a very small number of clusters. You carefully match clusters on a few covariates and randomize within pairs. It creates excellent balance and can also increase statistical efficiency, but the downside is that it's rigid. Matching must be done well, and you have to use paired statistical methods in the analysis. Always, always, always account for the design in a model, and that's true in every area of research design, right? Even in regular individually randomized trials, if you stratify, you want to include that stratification variable in the analysis because the stratification, yes, it's important for balance and for biases, but it's also potentially an explanatory variable which can help explain variability, thus increasing power. So in this setting, in implementation trials or in cluster randomized trials, we still have to account for the design in the model. You always account for a design in a model. Cluster randomized trials violate the assumptions of independent observations. Individuals with the same cluster are more similar, so intra-cluster correlation has to be accounted for analytically to avoid biased inference. This is why we would use something like mixed effects models, like random intercepts for cluster, to handle clustering well and estimate cluster level variability. Generalized estimating equations are another option when population averaged effects are desired, and fixed effects for clusters are occasionally used, particularly with small numbers per cluster. Ignoring clustering underestimates standard errors and inflates type 1 error rates. Another word on that I want to add is that I often get asked, how do I know whether I should use a fixed effect or a random effect for my cluster? This is a very common question. And honestly, it's not one that has an answer which is always right or always wrong. The way I go about this is if I want to make inference specifically to the few clusters I'm working with, like maybe schools in one district versus schools in another district or something like that, then I'm going to treat them as fixed effects. But if these are a random set of clusters that I want to generalize inference to a larger set, then I'm going to think of them as random effects. Okay. We may need robust standard errors or stratified standard errors. Even if you use regression models, the standard errors may not account for the correlation structure unless you specifically adjust for it. So cluster robust or sandwich standard errors help mitigate this, and this is what we see in GEE or ordinary least square settings. Stratified standard errors or matching considerations are also important when stratified randomization or matched pairs are used. The analysis must always, always, always align with the randomization strategy. Okay, so now I'm going to talk more specifically about the stepped wedge cluster randomized trial. And this is a type of cluster randomized trial in which all clusters eventually receive the intervention. What is random here is not whether the cluster gets the intervention, it's the timing of when they receive it. It's randomized and staggered. This design is particularly useful in implementation science when the intervention is already believed to be beneficial or standard of care. It's difficult to withhold from certain groups long term, or logistically rolled out over time, maybe due to resource limitations or training phases. So if you have an implementation of an intervention, but you've only got a few people who can deliver the training, they can't train many groups at once. So it's got to be limited in terms of doing one at a time, maybe. So this would be a great design for that. How does it work? At the start of the trial, no clusters receive the intervention. So these are both examples of stepped wedge cluster randomized trials. This one has a transition phase. I'm going to describe it. But what's important to note is that at the beginning, all of the clusters are white, which means they do not yet have the intervention. When they get the intervention, it's when it's shaded dark. Okay? So at the beginning, no clusters have the intervention. At each subsequent time period, which are the steps, so on the rows we have clusters, on the columns we have steps. Each subsequent time period, a randomly selected set of clusters crosses over from the control to the intervention. This continues until all of the clusters are eventually in the intervention arm. Outcome data are collected at each step from every cluster, allowing for both between and within cluster comparisons. That's pretty cool. Because each cluster provides data in both the control and the intervention periods, the design increases statistical power because we have within cluster comparisons. This is even better when within cluster correlation is high, because we get more precision of estimating that treatment effect. However, it requires adjustment for time effects in the analysis, assumptions about the stability of underlying outcome rates, careful attention to time-varying confounding, but this design is increasingly used in health system evaluations, policy, implementation studies, and service delivery interventions. So these diagrams show a classic complete step wedge cluster randomized trial where clusters cross from control to intervention, that's the one on the left, at different randomized time periods while outcomes are measured continuously. The stepped pattern arises because each cluster transitions at a different time, or each of these groups could be a set of clusters if we have a lot of clusters. Clusters are sometimes in a transition period immediately after crossover. Maybe this is the time it needs to train the staff at the clinic, right? And so that's where we have transition periods incorporated as well. This may or may not be included in the analysis depending on the intervention. Because each cluster functions as its own control before receiving the intervention, stepped wedge cluster randomized trials offer within cluster comparisons, improving efficiency, especially when cluster level variation is large. And since all clusters eventually receive the intervention, this design is appealing in context with either ethical or logistical needs to roll out the intervention to everybody. However, the design necessitates statistical control for time trends That is, changes unrelated to the intervention that occur over time. We call these secular time trends. So why choose a stepped wedge cluster randomized trial? There's several reasons why this design is becoming increasingly popular in implementation science and health services research. I first learned about this design about 10 years ago, and it was very, very rare. Now I'm seeing it all the time. It ensures that all clusters eventually receive the intervention. That is a really good thing, right? Providers, or clinics, when they're choosing to be part of an investigational study, they want to know that they're going to benefit from they're going to potentially get a beneficial intervention, right? So this is the hallmark of stepped wedge designs. If there's already belief, even from preliminary evidence, that an intervention is beneficial, then it may be unethical or politically unattractive to deny it permanently to a control group. A stepped wedge design offers this compromise: staggered randomized rollout while still allowing for rigorous evaluation. It's ethically appealing when withholding it is problematic. For interventions targeting health equity, access to care, or patient safety, investigators may face ethical considerations about assigning some clusters to never receive the intervention. The stepped wedge avoids this by ensuring eventual exposure to the intervention for every cluster. It facilitates phased implementation in a real-world setting. In many health systems, it is logistically impossible to ever implement a new intervention in all clinics and all systems simultaneously. The stepped wedge design works well when resources such as training staff or installing new software constrain the speed of a rollout. Maybe the intervention requires equipment that we don't have tons of, right? So it allows us to be able to do this in steps. It increases power in high intraclass correlation settings. So when outcomes are highly correlated within clusters, stepped wedge designs can be more powerful than the parallel arm cluster randomized trials when the within cluster comparisons help control for site level confounding. And it's useful for evaluating service delivery and policy interventions. Stepped wedge trials are well suited to interventions at the health system level, like care pathways or clinical decision support tools or health policy changes, where rollout is naturally phased and cluster randomization is more appropriate than individual level randomization. But there is caution. There's no free lunch. Everything worth having comes with a possible consequence, right? The caution is that despite all of these benefits, stepped wedge designs are not always the best choice. They require longer study duration, careful attention to secular trends over time, and appropriate analytic methods that adjust for time and clustering. So there are two kinds of stepped wedge design. They can be implemented in two different ways, I should say. One is a cohort or cross-sectional, and the other, one is cohort, one is cross-sectional, and the choice has major implications for design. Thank you. Thank you. So there's two ways of implementing this, cohort or cross-sectional. The choice has major implications for design, logistics, analysis, and interpretation in implementation science trials. In a cohort design, the same participants are followed over time, from pre to post intervention. So in each of these little steps that I showed you last time, here, in each of these boxes, you've got the same people, always, from step to step, right? So they're followed longitudinally. This allows for not only within cluster comparisons, but within person comparisons, offering high statistical power and greater control for individual level confounders. This is ideal when the outcome is longitudinal, like behavior change or disease progression, or if the intervention is designed to have a persistent effect, meaning we want it to last over time. So The pros here is that it gives us more precise estimates due to the within subject control, increased power with smaller sample sizes, and we can assess individual trajectories over time. That's great. But the cons: it requires intensive follow-up, increasing cost and complexity. There is a really high risk of missing data due to attrition or loss to follow-up. You lose a patient, you lose them everywhere, right? And there's potential for time-varying confounding, especially if implementation is slow. In a cross-sectional stepped wedge cluster randomized trial, different individuals are measured at each time point. For example, think patients visiting a clinic during a time window. This is simpler logistically and better suited for service delivery evaluations where the unit of intervention is a system or a site, not an individual. We also must be able to measure the outcomes quickly, right away. We're not waiting over time. The pros: data collection is simpler, especially when individual tracking is not feasible. There's lower participant burden. They don't have to be part of the study for very long, and easier IRB approval. It's useful for policy evaluations, acute outcomes, or public health interventions. The cons: there's no within-person comparisons, so it does require larger sample sizes to achieve equivalent power because you're not comparing within person. You have the between-subject variability affecting your standard errors for the treatment effect. There's greater dependence on assumptions about between-person comparability across time, and it's vulnerable to secular trends, so careful adjustment for time is critical. In implementation science, we use cohort designs when we're implementing behavioral interventions targeting chronic care or expect long-term individual effects. We use cross-sectional designs where the intervention is site level, affects workflows, or individual tracking isn't feasible. For example, electronic medical record-based outcomes. Okay, so here's an example of a cohort stepped wedge cluster randomized trial. The reference is at the bottom. I know it's very small, but again, you'll have my notes so you can see it. The full title of the study is called Managing Hypertension Among People Living with HIV, an implementation trial in Nigeria. It's called MAP-IT. This is a stepped wedge cluster randomized trial cohort design. So it's following people over time. The setting is 30 primary health centers in an area of Nigeria, the Akwa Ibom state, and the duration is 7 steps over 31 months. So you see all of the 31 months here and the 7 steps. The sample size is 960 people living with both HIV and hypertension. And there's about 30 on average per primary health center system. The intervention is a practice facilitation model to improve hypertension control among people living with HIV. There are trained facilitators trained facilitators supporting the primary health center staff in implementing standardized blood pressure screening protocols, task shifting for hypertension management, evidence-based treatment guidelines, and patient tracking and retention strategies. The implementation outcomes use that RE-AIM framework that we talked about last time, where we deal with reach, the proportion of eligible HIV adults with hypertension reached, the effectiveness, the blood pressure control improvement over time, the adoption, the primary health center engagement with the intervention, the implementation fidelity, the protocol adherence and facilitator activity, and the maintenance, continued blood pressure monitoring, and post-intervention period. The key features: this was a stepped wedge rollout across 30 primary health centers, and they all eventually received the intervention with rollout randomized by step. It was cohort-based, so the patients were followed longitudinally for blood pressure outcomes. It addresses that dual burden of HIV and non-communicable diseases in low and middle income countries. It had strong ethical appeal because no primary health center was denied the intervention. They were all able to get it. Why does this matter for implementation science? This is an example that demonstrates a logistically feasible, ethically favorable, and statistically efficient approach to system-level interventions. It shows how task sharing and practice facilitation can improve chronic care in resource-limited settings. And it offers a real-world template for stepped wedge cluster randomized trials in health system strengthening efforts. Here's another example, and this is of a cross-sectional stepped wedge cluster randomized trial. It's called the EPIC trial. It's a prime example here, and it evaluated a perioperative care bundle rolled out across 90 hospitals in the UK. Patients undergoing emergency laparotomy were assessed during each time window, with new individuals sampled each period. So this is now, we're not following the patients over time. Each period is new patients that went through this emergency procedure. The study used routinely collected data and had no longitudinal follow-up of patients. The outcome of interest was 90-day mortality. Are they alive or dead at 90 days? Measured through hospital records. To determine whether a multifaceted quality improvement intervention could improve survival for patients undergoing emergency laparotomy in these hospitals. This was the National Health System hospitals in the UK. So that's what was of interest, if this quality improvement intervention would improve survival or the probability of being alive after 90 days. The study design was a stepped wedge cluster randomized controlled trial across 93 National Health Service hospitals in England and Wales. Each site acted as its own cluster. Every site received the intervention, but implementation was staggered over time based on the enhanced perioperative care for high-risk patients, or the EPIC quality improvement collaborative model. The intervention itself was a package of evidence-based care elements, including risk assessment, timely surgery, early senior involvement, and critical care. The local quality improvement teams received training and support, and the use of the model for improvement and plan to do study act cycles. Again, the primary outcome was 90-day all-cause mortality after emergency laparotomy. The reference will be in my notes if you would like to look at it. The main findings is that there were no significant improvements in 90-day mortality. The adjusted odds ratio from the analysis was 0.93, with a confidence interval that went from 0.8 to 1.08, so it was not statistically significant. The secondary outcomes were length of stay, readmission rates, and complications, which also failed to show significant benefit. The implementation fidelity varied significantly between hospitals. Qualitative data showed challenges in the capacity to implement change, sustain engagement, and time and resource constraints. So while the intervention was very well designed and evidence-based, the real-world implementation challenges limited its effectiveness. And this is important, because in the real-world settings, it didn't work. This highlights the importance of implementation science. The success of interventions depends not just on design, but also on local context, capacity, and engagement. So the conclusion is that the EPIC Quality Improvement Program did not reduce mortality after emergency laparotomy. Future improvement efforts should incorporate more intensive support for implementation and address system-level barriers. Not there yet. There we go. Thank you. Okay. So I'm going to just a little bit about power in cluster randomized trials. This differs significantly from individually randomized trials. So in cluster randomized trials, individuals are grouped into clusters such as hospitals or clinics. The power depends not only on the total sample size, but also on the number of clusters and the intra-cluster correlation coefficient. And as we saw, even small ICCs can inflate the design effect pretty significantly and reduce the effective sample size. The number of clusters often has greater impact on power than the size of each cluster. So designs like stepped wedge or having unequal cluster sizes can further complicate calculations, often requiring simulation or advanced statistical tools. These things are rarely done in closed form. They're done with simulation, often. So some power formula basics. The design effect, again, quantifies how much the correlation within clusters reduces this effective sample size. We've already talked about the calculation where we have M being the average number of participants per cluster. And this effect adjusts our total sample size to reflect how much real or effective information we're getting. We've talked about how with a low sample size, we can have significant increases with a low ICC, we can have significant increases in the design effect, meaning you need to have many more participants in the sample size compared to a non-clustered design to achieve the same power. So power considerations in stepped wedge cluster randomized trials. Here in stepped wedge cluster randomized trials, clusters transition from the control to the intervention, so the power is affected by how many time periods or steps are included, the number of clusters, as well as the timing of the crossover. So there's many factors that affect our power. Additionally, temporal trends over time, and the ICC will again influence the outcomes. So stepped wedge cluster randomized trials can offer higher power than parallel cluster randomized trials if the crossover is timed well and the intra-cluster correlation is managed appropriately. But these designs require careful modeling of the correlation structure across time and clusters. Okay, so in a stepped wedge cluster randomized trial, power and sample size are so strongly influenced by how outcomes are measured across time. And this differs significantly between the cohort and the cross-sectional designs. In a cohort stepped wedge cluster randomized design, again, we follow these same individuals across multiple time periods. This means that the within cluster correlation includes within cluster correlation over time as a result. The correlation structure becomes even more complex, for example, individuals nested in clusters across time, but you gain efficiency because you can detect changes within the individuals as they move on the individual level from control to intervention periods. The design tends to require smaller sample sizes overall, assuming reasonable follow-up and retention. However, cohort designs are more vulnerable to missing data and attrition, especially over long periods. If follow-up is poor or we're dealing with populations that are really hard to keep engaged, the benefits of a cohort design may be lost. In contrast, a cross-sectional stepwise cluster randomized trial collects new individuals at each time period, meaning there's no repeated measurement on the same person. This simplifies the correlation structure. We only need to account for intra-cluster correlation, but since each time point is a new sample, there is less within unit consistency, so the power per observation becomes lower. Thus, to achieve the same power, we often need larger sample sizes, especially if the ICC is high. So in summary, the cohort design is statistically more powerful, but operationally harder. It's more demanding. The cross-sectional design is simpler, but may require more participants. The choice between these should be driven by study goals, feasibility of follow-up, data burden, and the nature of the outcome, whether it's a repeated measures outcome or a one-time assessment. Simulation is often used in either case to optimize power considerations, especially when ICCs are uncertain, so we want to compute them or estimate them over a range, or when time trends are expected. Specialized software is essential for accurate power estimation in cluster randomized trials. In R, we have packages and I have them all listed here, like CRT size for parallel cluster randomized trials, and SWCRT design for stepped wedge designs. STATA and SAS also have functions for this, but when the design involves unequal cluster sizes, complex correlation structures, or stepped wedge crossover, analytical solutions often fall short. This is when simulation-based power calculations become particularly useful and flexible. Here is simple R code snippets using the SWCRT design package. First, you define the design using the SW design, specifying the number of clusters, periods, and cluster size. It's all in here. Then you estimate power for a given effect size and significance level. This tool can accommodate a variety of stepped wedge configurations and be extended to include time trends or other covariates. But for more complex settings, which usually ends up being the case, you want to run a full simulation. Okay, so choosing cluster size versus number of clusters. How do we do that? This is a very common design question in cluster randomized trials, which is whether we increase the number of clusters or increase the size of each cluster. Now, sometimes you don't really have a choice. You may not really have more clusters to choose from. Oh, thank you. Very much, thank you. So we ask whether or not we should increase the number of clusters or increase the size of each cluster. Sometimes you have a choice, sometimes you don't. But statistically, increasing the number of clusters almost always has a greater benefit for power than does simply enlarging the existing clusters. And the additional benefit gets bigger and bigger the higher that ICC is. This is because adding individuals to a cluster doesn't provide as much new information when those individuals are highly correlated due to high intracluster similarity, or high ICC. Once the cluster size exceeds a moderate number, maybe 30 to 50 participants, the marginal gain in precision diminishes substantially. Instead, adding new clusters gives us new units of randomization, which contributes more to overall power. Logistics plays a big role. Smaller clusters may be easier to manage, and sometimes it's more cost-effective or administratively feasible to just increase cluster size instead of adding new sites. Recruitment constraints, IRB approvals, and geographic dispersion may limit the number of clusters you can include. Ultimately, it's a balance between statistical efficiency and real-world feasibility. Most sample size tools for cluster randomized trials, including simulation-based methods, allow you to vary both the number of clusters and the cluster size, so you can kind of explore these, tuning things to get the most efficient design for your context. I would encourage you to always aim for more clusters over larger ones if you can. So this slide illustrates a fundamental principle in the design of cluster randomized trials. Power increases more efficiently by increasing the number of clusters than by increasing the size of each cluster. So here you have the number of clusters or participants per cluster, the clusters or participants per cluster here, and then you have the power here. And so the yellow line shows how power increases as you add more clusters, keeping the cluster size consistent. So that's this yellow line. We see a steep and nearly exponential rise at first. Power approaches the commonly desired 80% threshold fairly quickly. This is because each cluster adds a new unit of randomization, which is what truly drives power in these cluster randomized trials. But the orange line, so for the yellow line, this means number of clusters with a fixed cluster size. For the orange lines, it means cluster size for the fixed number of clusters. So it means something different for the two lines. The orange line shows power as we increase the number of individuals within each cluster, holding the number of clusters fixed. At first, there's some modest gain in power, but it very quickly flattens out. This is due to intra-cluster correlation that we talked about before. Doubling the size of a cluster does not double your effective sample size. So when planning the trial, you have the option. Invest your resources into recruiting more clusters as often as you can, rather than adding more participants per cluster. Now, this plot does assume fixed ICC and equal cluster sizes. In reality, unequal clusters and variable ICCs may shift these curves, but this is for illustrative purposes to get you to understand the general pattern. Simulation studies are very helpful when designing the optimal design under more complex assumptions. So as an overview, for modeling cluster randomized trial data, observations within the same cluster, as we know, are correlated, and ignoring this leads to underestimated standard errors and inflated type 1 error. So there's two major modeling frameworks that we use commonly that account for this. Mixed effects models. These introduce random effects for clusters, allowing individual outcomes to vary around a cluster-specific mean. This is often referred to as cluster-specific or subject-specific approach. The subject here is the cluster. Generalized estimating equations model the marginal mean across the population, accounting for correlation using a working correlation matrix. This gives population averaged estimates. The choice depends on the research question. Are we more interested in knowing the effect for an average individual in a cluster from a mixed model, or for the average effect across the population? That would be for using a GEE. So this slide helps visualize different ways we can model data when it has a hierarchical or clustered structure. This is essential in cluster randomized trials. So the top left here is fixed effects. This is like simple linear regression. Here we assume no clustering. Every individual observation is treated independently. There is a single intercept and a single slope. And that's estimated across all the data. This would be inappropriate, wildly inappropriate, in a cluster randomized trial where individuals within a cluster share characteristics leading to correlated outcomes. This top right is mixed effects that has a random intercept but a fixed slope. So you see the lines are parallel to each other. This model adds a random intercept for each cluster, allowing each group to start at a different baseline. However, it assumes the same treatment effect across all clusters. This is often a good first approach for a cluster randomized trial where we expect baseline differences between clusters, but a consistent treatment effect. The bottom left is a mixed effects model with a fixed intercept and a random slope. This is not as common in cluster randomized trials, but conceptually important. All clusters start at the same point, but the treatment effect is allowed to vary in the modeling across clusters. This might be useful when intervention delivery is uniform at baseline, but has variable impact. The bottom right is random intercept and random slope. Here, both intercepts and slopes vary across the clusters, so the interpretation is that each cluster has its own baseline level and its own treatment effect. This model is the most flexible and often used when we suspect heterogeneity in both baseline and treatment effects. In stepped wedge or pragmatic cluster randomized trial, this model may better reflect real-world variability. So in cluster randomized trials, accounting for clustering is critical for valid inference. Mixed models allow us to do this, modeling the hierarchical structure directly, improving both power and estimation. But the choice of random effects should be grounded in design knowledge, ICC estimates, and realistic assumptions about how clusters behave. So this slide, it reinforces the concept of the random intercept and slope model, which is a powerful tool for analyzing data from a cluster randomized trial and other hierarchical structures. You've probably seen this before. What's new is just the application. So breaking this down, Yij is the outcome for an individual J within cluster I. Alpha is the fixed intercept, the baseline outcome for an average cluster when the predictor is 0. Predictor X is 0. Ui is the random intercept. It allows each cluster, notice it's indexed by I, to have its own baseline level. It captures between cluster variation at the starting point. Beta is the fixed slope. It represents the average effect of the predictor X across all clusters. And VI is the random slope. It allows the relationship between X and Y to vary across clusters. For example, one clinic might respond strongly to an intervention while another might not. And then epsilon ij is, as you expect it to be, the individual level error term. This model captures both types of heterogeneity seen in cluster randomized trials, baseline differences between clusters, and differences in the strength of the intervention effect. We assume here that ui is a normal random variable centered around 0, and VI is also a normal random variable centered around 0, and they each have their own variability. The variances and their covariance tell us about the extent of variability across clusters. This model is commonly fit using mixed effects regression or multivariable modeling and is especially relevant in implementation and pragmatic trials. Generalized estimating equations are also used for cluster randomized trials. This is widely used, especially when the outcome is binary, count, or otherwise not normally distributed. It is a marginal model, GEEs, which means it estimates the population averaged effect of treatment rather than estimating effects at the cluster level. This contrasts with mixed effects models, which are cluster-specific or conditional models. For many public health and policy interventions, the population average effect is the quantity of interest, making GEE a natural choice. A key strength of the GEE is it accounts for within-cluster correlation, which is crucial in cluster randomized trials because of that fact that responses from individuals within the same cluster tend to be correlated. The correlation is modeled, however, using something called a working correlation matrix. This is such as exchangeable, meaning equal correlation among all members of a cluster, independent or even unstructured. GEE is robust to misspecification of the structure, meaning that even if the working correlation that you start with is not quite right, it does not cause bias in the parameter estimates. They're still consistent as long as the mean model is correctly specified. Inference is based on robust, or what you might have learned to be sandwich standard estimators, which adjust for the correlation between observations within clusters. One limitation to note is that GEE heavily relies on asymptotics, large sample theory. So it performs best when there are a relatively large number of clusters. In cluster randomized trials with very few clusters, results might be biased or way overly optimistic unless corrections are applied. So GEE is implemented in many software packages such as GPAC in R or ProcGenMod in SAS, making it accessible and a practical approach. So this slide gives you a kind of, when should you use which one, right? So you'd use GEEs, and how should you use each one? GEEs estimates the average effect across all clusters, modeled as mean response over populations, accounts for clustering using working correlation, provides robust standard errors, and it's best with a large number of clusters. Where mixed effects models are cluster specific, they estimate effects conditional on the cluster, they include random intercepts and potentially slopes, they account for cluster variation directly, and the inference is model-based, standard errors, and it's better for small sample of clusters or intra-cluster variation. This slide provides a concrete example of a GEE model used for analyzing data from a cluster randomized trial. There it is. For a cluster randomized trial where the outcome is binary. For example, whether a patient adhered to medication. So did they adhere or did they not? It's a binary outcome. YIJ here in this model specification is the outcome for the ith individual in cluster J. Here we model the expected value of Y on the logit scale. So it's binary data, we're modeling it on the logit scale, and that's appropriate for binary data. The model includes an intercept for beta 0, which is the baseline log odds, and a treatment indicator at the cluster level, since entire clusters are randomized. Optional individual level covariates, Xij, can be incorporated for better precision. The GEE approach does not specify a random effect, but it rather accounts for clustering through a working correlation matrix. The most common is exchangeable, assuming equal correlation among all individuals within the same cluster. Importantly, the estimate of beta 1 represents a population averaged treatment effect. That is, the average effect across all clusters and all individuals, not conditional on any specific cluster. Robust sandwich standard estimators are used for inference and are valid even if the working correlation structure is misspecified, provided the mean model is correct. So this visual shows 4 common types of working correlation structures used in GEE. Exchangeable is the first one. All off-diagonal elements are the same, meaning every pair of individuals in the cluster is assumed to have the same correlation. Independent, no correlation is assumed among observations within a cluster. This is the simplest model structure and often used as a baseline. Autoregressive 1, AR1, is an autoregressive structure where correlation decreases with the distance or time lag between observations. This is typical for longitudinal data. And then unstructured, where each pairwise correlation is estimated separately. It's flexible but data intensive and rarely used in cluster randomized trials. The choice of the correlation structure can improve efficiency. If you get it right as your working correlation, you're going to have the most efficient estimation in a GEE, but it is robust to misspecification as long as the mean model is correct. So this slide outlines the assumptions underlying the use of GEE and mixed effects models in cluster randomized trials. GEE focuses on population average effects and requires that the mean model is correctly specified. While it does use a working correlation structure to account for within cluster correlation, that structure does not need to be perfectly specified. It only affects efficiency, not validity. However, GEE relies on large sample theory, and small numbers of clusters can lead to biased standard errors if not corrected. In contrast, mixed effects models estimate cluster-specific effects and require assumptions about both fixed and random parts of the model. Most notably, they assume that random effects are normally distributed. These models handle small cluster counts better, particularly when random variation between clusters is important to model explicitly. Both approaches assume independence between clusters and assume that missing data are either missing completely at random or missing at random, depending on the estimation method used. In GEE, estimation is performed using something called quasi-likelihood methods, typically implemented using iteratively reweighted least squares. GEE does not fully specify the outcome distribution. It focuses on estimating the mean structure, and it uses a working correlation matrix, as we discussed before, to account for the intra-cluster correlation, making it robust to distributional assumptions. But in mixed models, particularly generalized linear mixed models, estimation is far more complex. When the outcome is binary or count, likelihood functions do not have closed form solutions, so we have to use approximations like Laplace approximations, penalized quasi-likelihood, or adaptive quadrature. These methods depend more heavily on the assumed distributions of both outcome and random effects. The takeaway here is that mixed models are more model-based and require stronger assumptions, while GEE provides consistent estimates under weakened assumptions, focusing only on the mean model. So this slide provides a conceptual and visual distinction between the GEE and mixed effects models. On the left, we can see how GEE focuses on estimating a single average treatment effect. It does this by modeling the mean outcome across all clusters and all individuals, adjusting for the clustering through that working correlation structure and sandwich estimation. Think of it as saying, If we gave this treatment to the whole population, what would the average effect be? But on the right, the mixed effects model, sometimes called multi-level or hierarchical, allows each cluster to have its own intercept and possibly its own slope. The approach is helpful when we want to know how treatment effects vary across clusters or when cluster-level heterogeneity and inference is of interest. Importantly, the choice between which approach depends on the scientific question and the data structure. If you're primarily interested in overall effectiveness at the population level, GEE is your most appropriate choice. If you're interested in how effectiveness differs by cluster and what the between cluster variability is, or if there are few clusters, mixed models may be better. Oftentimes, statisticians will choose to fit both and do sensitivity checks. It's useful to see whether or not the inference is affected by the approach. When it's not, you have more confidence in your results. And so this is just a visual that gives you a summary of the key considerations that I've just talked about. Choosing between a GEE and mixed effects model, it's a nice cheat sheet. And the table helps guide model selection depending on study aims, sample size, and assumptions you're willing to make. Choosing the right modeling strategy depends on the research question, design, and data characteristics. If your goal is to understand how the intervention works in each cluster or to model heterogeneity, mixed effects are preferred. If you're primarily interested in the overall effect in the entire population, a GEE may be a better fit. For complex designs like stepped wedge trials, mixed models may be more flexible, but a GEE can be used. And so this is just simple R code fitting a GEE model using the GPAC package. The outcome's a binary variable like success or failure. The treatment is a cluster level indicator, intervention or control. The covariate represents any additional covariate or individual level covariates. The ID indexes the cluster identifier, so the GEE can account for intra-cluster correlation. The family obviously is the family of the link function, so if it's binomial, you would probably use a logit link, and that specifies a logistic regression function. The CORSTR is the statement that is exchangeable, assuming a constant correlation between observations within the same cluster. So that's the correlation structure specification for the working correlation matrix. And the output includes estimated population average treatment effects and robust standard errors. And then this is our code fitting a mixed model using the LME4 package. Like before, outcome's a binary variable and treatment is a cluster level indicator. The key difference here is that this random effect, which is in here, and introduces a random intercept for each cluster. This allows for the between cluster variability in the baseline outcome level. The glimmer function fits a logistic regression model that is conditional on the cluster. The resulting estimates reflect cluster-specific treatment effects, which may differ from population average effects from GEE. The random intercepts obviously help account for the unobserved heterogeneity between clusters. Okay, so this is a simulated data set that here we're generating a simulated data set mimicking a typical cluster randomized trial design. The binary treatment is assigned at the cluster level, and each cluster also has its own random effect. The outcome in this simulated data is binary and depends on the treatment and covariate effects plus the cluster effect. And this slide outlines the two methods we could use to analyze the simulated cluster randomized trial data. The GEE estimates the marginal effects while the GLMM models conditional effects. Their interpretations differ, which both affect estimates and inference. And here is the code. Again, I don't know that you, well, no, you didn't. There's the code. It compares how to fit the GEE versus the GLMM model on that simulated data. You can use this code and substitute real data, or you can use it to generate simulated data and fit models so that you can see how they would perform under different assumptions. The GEE model is population average, while the GLM model includes the random intercept for cluster and it eliminates cluster-specific effects, and estimates, cluster-specific effects. In practice, this choice affects interpretation, as we've already talked about. So this slide compares GEE and GLMM models both visually and numerically. The top panels show the predicted probabilities of outcome from each model stratified by treatment group. So you have 0 and 1, the two different colors, right? 0 being the control, 1 being the intervention, and it's plotted across a covariate. The left panel shows the GEE model's marginal predictions, which are flatter and more conservative, representing average population effects. It's hard to see, but the right panel shows the GLMM model's conditional predictions, which are a little steeper in the way that they're going upwards, reflecting the additional variability captured by cluster-specific random effects. Below the plots is a table comparing coefficient estimates, standard errors, and p-values from both models. So these are the same data being fit to two different models in the simulations. Note how the GLMM coefficients are larger in magnitude compared to the GEE, particularly for the intercept and the treatment effect. This reflects the well-known difference in interpretation. GEE estimates are marginal, while GLMM estimates are conditional on cluster. Despite these differences, statistical significance is maintained for all variables in both models in this simulation example. So this interprets the model output from the table I just showed you, summarizing the key differences between the GEE and the GLMM. Again, the GEE is modeling that population averaged mean response, while the GLMM models the conditional cluster-specific response. And because of this, the GEE estimates tend to be closer to the null compared to the GLMM, which shows larger treatment effects. The treatment interprets the output from a logistic GLMM with a random intercept for cluster. The intercept of negative 1.508 is that baseline log odds of the outcome for a patient in a baseline cluster with covariate being 0. And the treatment coefficient reflects the log odds ratio within clusters, a more extreme effect than in the GEE model. And this summarizes the inferential differences between GEE and GLMM models. While both models show treatment and covariate effects, GEE is often used for average effects across the population, and GLMM for effects within a typical cluster. Their estimates, standard errors, and interpretation differ. So here's a real-world example of a hybrid-style cluster randomized control trial evaluating something called a WASH intervention in Philippine schools. I have the reference on top. The study randomized 15 schools and delivered a bundle intervention involving health education and provision of hygiene supplies. The primary outcome was observed hand-washing behavior, analyzed using multi-level logistic regression to account for clustering by school. Hand hygiene behavior significantly improved with an adjusted odds ratio of 2.34. Hydration and health literacy also showed positive effects. All analyses accounted for school-level clustering, including multi-level models, and these results demonstrate how hybrid trials in the real-world educational settings can show both health and behavioral improvements, supporting implementation science goals. This slide expands on one of the most common statistical pitfalls in cluster data analysis, failing to account for the clustering. When clustering is ignored, for example, when patients within clinics or students within schools are analyzed as if they were independent, it leads to underestimation of standard errors. Why? Because observations within the same cluster are often more similar to those in different clusters. So smaller standard errors make effects appear to be more precise than they truly are and inflate type 1 error, detecting a statistically significant effect when none truly exists. The analysis will assume more information is available than actually is, violating the independence assumption. So these box plots compare simulated outcome data from two conditions. On the left, we have cluster data where observations within clusters are correlated. And on the right, we have independent data where no such correlation exists. The takeaway, cluster data often show less variability within clusters because of the ICC, and analyzing as if it is independent is wrong. You underestimate the standard errors, leading to inflated type 1 errors. So to avoid this, use models that are sensible and account for the ICC inherent in the data structure. So when analyzing trials or studies with few clusters, like maybe 4 to 10 sites, standard mixed models or GEE methods may produce biased standard errors and inflated type 1 error rates. To address that, you could do cluster level analyses, meaning aggregate data at the cluster level and compare group means. This avoids dependence across individuals, but reduces precision due to fewer units. So the clusters become your sample size, especially useful when you have very few clusters, like less than 10. Avoid naive individual level models at all costs. Do not ignore the clustering. Apply small sample corrections. So if using linear mixed models, you can apply Kenwood-Roger or Satterwhite approximations to correct degrees of freedom. For GEEs, you can consider biased corrected sandwich estimators, or you can use permutation or randomization tests. These tests always maintain correct type 1 error rates empirically, even with few clusters, by using the randomization distribution instead of relying on asymptotics. Best practices for cluster randomized trials are in this slide here. The slide summarizes best practices that should guide both the design and the analysis of cluster randomized trials. These practices aim to ensure scientific rigor, transparency, and interpretability. So one by one, account for clustering in the design and analysis. We estimate and report the ICCs. We balance the clusters on key covariates, and we talked about ways to do this, like stratified randomization or constrained randomization. We use appropriate analytic methods, GEE or GLMM, minimize contamination across clusters in the design, report the number of clusters and cluster sizes clearly, and pre-specify analyses. These best practices are not just about statistical rigor. They enhance reproducibility, transparency, and ultimately the impact of cluster randomized trial findings on real-world practice. Journals, funders, and regulators increasingly expect adherence to these standards. And that is all I have. Any questions? Any questions? Y'all hungry? You want to go to lunch? Okay. Well, you have my email address. If you want the slides or you have any questions, please let me know. And if you speak slowly, I'll even understand them in Spanish, but you have to speak slowly for me. Okay. That's it.